Hi everybody, Justin here from chemistrynotes.com, and today we are continuing with section 5 gases. The last video we learned about the individual gas laws, and then we combined them all into the combined gas law, and then we also were able to define the gas constant R and come up with the ideal gas law. So today we're just going to do a bunch of practice problems where we don't know what law or laws we need to apply. So here's your first example, and we'll have to read the problem to decipher, is this a gas law problem? Is this a combined gas law problem? Or is this an ideal gas law problem? So here's the first example. A sample of H2 gas occupies a volume of 8.56 liters at a temperature of 0 degrees Celsius and a pressure of 1.5 atmospheres, 1.5 atm. How many moles of hydrogen are present? Well, we see that it's giving us a volume of 8.56, temperature of 0, pressure of 1.5, and it wants moles. So there's no situation 1, situation 2. They're just giving us a bunch of values for all of the variables in PV equals nRT. So PV equals nRT rearranges to N equals PV divided by RT. I plug all of the numbers in. Luckily, we have all the appropriate units that match up with our units for R, and the answer is 0.57 moles of H2. So the second example here on page 1 of our notes says, calculate the volume of 0.845 moles of nitrogen gas at a pressure of 699.2 torr and a temperature of 315 Kelvin. So we want to find V, volume. We're given moles, we have a pressure P, and we have a temperature T. So I'm just going to make a list here of everything that I was given, and you see that the one that we're missing is volume. Now, N is in moles, perfect. T is in Kelvin, perfect. But our pressure is in torrs. I don't want torrs if I'm going to use the ideal gas law, remember? In our last video, we talked about units being specific for the ideal gas law. So I can quickly convert torrs to atmospheres, and then I'm going to use the pressure that I now have in atmospheres, and I'm going to solve for my volume. So page 2 of our notes here, we're continuing with the second example problem. PV equals nRT. We rearrange. I like to rearrange when it's still just the letters. V equals nRT over P. Plug everybody in. You notice what pressure I'm using? I'm using the pressure that's in atmospheres. And if you look at all of the units I've included here, everything cancels, and I'm left with only liters. 23.8 liters of N2. N2 is nitrogen gas. Now, here is a tip, a very important tip that I want to tell you guys about regarding these PV equals nRT problems. PV equals nRT problems don't typically have a situation 1 where there is a certain pressure and volume, for example, and a situation 2 where we have a new pressure and we're asked to solve for this new volume. PV equals nRT problems, there is no situation 1 and situation 2. There's usually just one situation. They give you pressure, they give you volume, they give you moles. You have to solve for temperature, etc. Okay? Now, before and after type problems, situation 1, situation 2, those I like to call before and after problems. Those usually require Boyle's law, Charles' law, Avogadro's law, or the combined gas law. Okay? So that's just a tip. That's not letting you know what type of sample problem is coming up next. Let's read the problem and see what law we need to use. Here it is. Example. A sample of methane gas with a volume of 38 milliliters at 5 degrees Celsius is heated to 86 degrees Celsius. You see how the condition has changed? It's heated to 86 degrees Celsius at constant pressure. Calculate its new volume. It also uses the phrase new volume. New volume implies that there used to be a V1 and now we need a V2. So we know that the ideal gas law is out. So let's just make a list of everything that the problem gives us. V1, 38 milliliters. T1, I convert Celsius into Kelvin, 278 Kelvin. V2, I don't know. T2, 86 degrees Celsius, I add 273, I get 359. This is Charles' law. V1 over T1 equals V2 over T2. I plug everybody in except for V2. And the way you solve for V2 is you cross multiply 38 and 359, and then you divide by 278. Cross multiply and divide, you get a V2 equal to that volume right there of CH4. Now I have a question about that last problem we just did. How come it wasn't necessary to convert V1 and V2 into liters? How come I was able to leave them in milliliters? Well, we were using Charles' law, right? V1 over T1 equals V2 over T2. As long as the V1 and V2 have the same units, I'm fine. Now, the kelvins, I have to make sure temperature's in kelvins, but for volume, I could have used liters, ounces, as long as they were both the same. Why is that? Well, there was no R involved. R, capital R, the universal gas constant, is only in PV equals nRT. And look at the units for R, 0.0821 liter atmosphere per Kelvin per mole. So whenever you're using PV equals nRT, you have to be specific about your units. That's why I didn't need to in the last problem. It was Charles' law, not the ideal gas law. All right, next example. Diborane gas, B2H6, has a pressure of 345 torr at a temperature of minus 15 Celsius and a volume of 3.48 liters. If conditions change, see that phrase? If conditions change such that the temperature is 36 degrees Celsius and the pressure is 468 torr, what will be the volume of the sample gas? Okay, so what will be the volume of the sample gas? Well, let's just make a list of everything that we're given here and figure out what it is that we need to solve for based on our list of all the stuff they gave us. P1, 345 torr. T1, minus 15 plus 273 equals 258 K. V1, 3.48 liters. Well, they also had if conditions change. If conditions change. It was actually, that was the actual wording. Such that, so now I have a T2, a P2, and I have to solve for V2. So this is going to be the combined gas law, except I don't have to include the N1 or N2 because the N1 and the N2, it's the same sample of gas. Same sample of gas, so N1 equals N2, it drops out. This is a combined gas law problem. P1 V1 over T1 equals P2 V2 over T2. I plug everybody in. You notice I can leave my pressures in torrs. That's because we don't have the universal gas constant R here. Okay, you only have to use specific pressure units of ATM when you're using the ideal gas law. So I cross multiply and divide, clean this up, or if you want, you can cross multiply and set them equal to each other. V2 equals 3.07 liters of diborane, B2H6, 3 sig figs. All right, another example here. We don't know what we're going to use. We're going to read the problem and then determine, do I need the ideal gas law? Is it combined gas law? Is it Boyle's law, Avogadro's law, Charles' law, etc.? So let's see what they give us. A gaseous sample contains 0.35 moles of argon at a temperature of 13 Celsius and the pressure of 568 torrs. Here comes that magic word, if. If conditions change, see? If it's heated to 56 degrees Celsius and a pressure of 897 torr, calculate the change in volume that occurs. Kind of a different wording there at the end. We'll come back to that. Let's just list everything right now, okay? Well, N, or possibly N1, is 0.35 moles. T1 is 13 plus 273 is 286 Kelvin. P1, 568 torrs. T2, 56 plus 273 is 329 K. V1 equals, I have no idea. V2 equals, I have no idea. So this is strange. We don't have any of the volumes. Well, we know N1 equals N2 is unchanged. It's going to drop out. And we need to find the change in volume. Well, the change in volume is simply V2 minus V1. So what I should probably do is do PV equals nRT twice. And then solve each of those PV equals nRTs for their individual V or volume values, and then subtract the two. So that's what you're going to see here in the last page of our notes for today. So PV equals nRT. I'm going to change it and call it P1V1 equals nRT1. Solve for V1. Moles is 0.35. R, 0.0821 liter atmospheres per Kelvin per mole. Temperature, 286 Kelvin. Now the P1, I have to use atmospheres because this is the ideal gas law. So it's 0.747 atmospheres. V1 equals 11 liters. Let's save that. Let's save the 11 liters. We're going to need it at the end. Just a little note here. This is how I got the 0.747 atmospheres, right? Started with what I given, 568 torrs, convert to ATM using the conversion factor. All right, let's solve for V2 the exact same way. P2V2 equals nRT2. So rearrange, V2 equals nRT2 divided by P2. Plug in all my values. You see the moles is 0.35 again. 0.0821 is R. 329 is my temperature. And that 1.18 ATM is my P2 converted to atmospheres. So what I end up with is a V2 value. If I multiply 0.35 times 0.0821 times 329 divided by 1.18, I get a V2 of 8.0. If you subtract V2 minus V1, you get a change in volume of negative 3.0 liters. That means the volume has decreased by 3.0 liters. All right, so I hope that this video of all the practice problems for ideal gas law, combined gas law, and then the individual gas laws, hopefully that clarifies some of the stuff that we learned in the last video. So if you like the way I do these handwritten notes, please hit that subscribe button. It's that little molecule you see popping up right next to my picture up here. And there's some other videos there that you might enjoy as well. So that's it for today, and have a great one.